Okay, today we have a tree problem. We have a tree. The tree is a graph where every node is connected. Twice or once. So then we have values at each node, and we have k number, and we asked how many like cuts we can make like this. So the individual connected component or subtree is sum divisible by k. The important part of this problem is that the entire tree sum is divisible by k. That means if we walk from some, I don't know, leaves like this and compute sum of visited nodes, and a sum happens to be divisible by 3, by k, that means the other part automatically is divisible by k because the entire sum is divisible by k. That means we can just scan the entire tree subtrees, and if we see any subtree sum divisible by k, we immediately make a cut, and this will give us the optimal algorithm for making as much cuts as possible. So what another hardness is that the tree given in a not very, I don't know, simple way. They are just like edges that connects nodes and values. There's not like typical node list of classes with links. It's just edges. So we have to make a tree. However, we're not given a particular order of the nodes, and that means that we don't know which node is the root. It can be any of this. However, this actually doesn't really matter. We can start with any node, and we can start with just 0, and I use parent to hint that we shouldn't go back to the parent. And this solution is depth first search. However, we also have, so I will shortly explain how depth first search works in tree. So we go down to each node, then we're going back, and we do this plus operation and comparing the sum. Then we're going back, and we come again down, back, plus operation, and back. So this is depth first search, and it computes the sum of the subtrees like this. However, we can go in it's in depth first search. We can go also in a breadth first search. The leaves are the nodes that have only a single connection. So we can track them and go from them up. And we can, like, when we go up, we just do plus operation too, and track if it's divisible by k. The implementation is not much very difficult. You just have to maintain the incoming in degree. It is an array size of current nodes, and it is a counter of how many nodes, how many edges each node have. And we do like minus minus operation, and then we compare if it is equal 0. This is a breadth search. So this problem is not very hard, however, it's marked as hard. The acceptance rate is pretty big. Let's look at the hints. Root is 0, however, it can be any node. It's not necessarily 0. So that's all. I solved this problem year before. Let's look at my best compressed solution. And here is one. This part is the same, and this part is a trick I used to write this one line. It is returning the actual result instead of sum, and the sum is tracked in the values. It's similar to the breadth search algorithm that I explained earlier. Just have to track sum somewhere, and then we should compare them to the divisible by k, and if it's divisible we add in 1, and DFS returns the total number of cuts or the total number of intermediate sums that are divisible by k.